Hello everyone, hope you're doing well. Welcome back to my channel. Today we are at day 14 for the March Daily LeetCode Challenge. First of all, a big congratulations because today we will be completing first 2 weeks. Okay, I mean we are completing 14 days now in this particular challenge. We've almost reached the first half of the March. So if you have been consistent till this point, definitely a big congratulations to all you. Okay, now coming to this question, let me summarize like what we have seen till now. See, from the last 2 to 3 days, we are seeing questions on binary search. Okay, we are seeing the questions on binary search, and today also it's a question on binary search. And let me tell you this: yesterday's question, that is, I'm talking about day 13 question. It was a FANG level interview question which we did using the binary search. Okay, so if you have not tried that, please do go and try that. And remember one more thing: when I say binary search, it see we are not searching something. Okay, it's just the idea that we are using of binary search. Okay, we are taking idea from the binary search and we are doing the search in such a way that we are like reducing half of the space in every iteration. Okay, that is the basic idea. Okay, we are not searching something in this case directly, but yeah, we are trying to find a value which the way, okay, the way the binary search does, we are reducing in every iteration, we're reducing half of the search space. Okay, we are like, yeah, exactly reducing the half of the search space. Okay, that is the basic idea that we are going to follow. Okay, so we are taking ideas from the binary search. So yep, this is the third question for in that row, third medium level question in that row. I will request please do go and see yesterday's question. Okay, it was a fang level intro question. And again, like coming to this question, if you saw yesterday's question, this will this definitely will look easy. So let us see what we can do here. So again, same thing like say this question, because the theory is slightly, we'll have to read, go through it properly. So I will request that please pause the video, go through it. Otherwise, the question link is in the description. Take it, then go through it. But the idea is very simple. We are given certain candies. Okay, the numbers that you're seeing are there basically piles. Okay, for example, this is a pile. Okay, this is a pile number one. Pile number one means in this particular pile there are 5 candies. Similarly, in this particular pile there are 8 candies. What they're asking you now is, see, you can divide these piles into sub piles. What that means is I can divide this, I can like break this pile into sub piles. What that means is, let us say it is 8. Okay, so 8 can be broken into 5 plus 3. Okay, so 5 will be a pile now and 3 will be a pile now. Okay, so we can create 2 piles from this sub pile. So similarly, we can create n number of sub piles from this. Okay, for example, see, all whole numbers it should be. For example, from this eight, we can create 8 different piles. Okay, as simple as that, and something like that. Okay, that is the basic idea. But the question is, we have to distribute even number of, that is, we have to distribute the same number of candies to each children. That is the first important constraint. Second is that we want to know the maximum number of candies each child can get. Okay, remember both of these are very important. All the child should get the same number of candies. K is basically represents the number of children. Okay, K in this case is represented by the number of children. Okay, yeah. Yep, there are k children in this case, right? Yeah. So we have to, like, first thing is same number of candies should be given to every children. Then we have to find the maximum number of candies that can be given. Okay, and exactly like that. Okay. So in this case, if you see, we can give 5 candies to each children. Okay, 5 will come from this. Okay, other 5 will come from this, and similarly other 5 will come from this. Okay. One more thing, very important thing is, which you should be knowing, that you cannot join two subpiles. Okay. Yeah, they have mentioned here, but you cannot merge two piles together. Remember that this is very very important. For example, if I break this 5, breaks 8 as 5 plus 3, then the remaining 3, right, that cannot be used again. Okay, as simple as that, because something is broken. So the idea is like it's a one way go. Okay, so once we break it, we cannot compile it, join or merge it again. Okay, as simple as that. So I hope you're getting the question. And one more important point is, like, let me show this case also. There's, see, one good test case that I've added. Let me show you that also. Yeah, this is the one. Okay, see, in this case, 1 1 15. So in the first pile there are 1 candy, in the second pile also 1 candy, in the third pile there are 15 candies, and there are 3 children. So obviously the answer is going to be 5 again, because all the candies are now going to come from this particular pile. So as you can see, the first two piles are not even used. Okay, in the actual distribution, all the candies that are being distributed is coming from this. Okay, 5 from this is going to the first children, and similarly 5 plus 5 plus 5 is going to all the 3 children. Okay, as simple as that. So what we will do is, you will try to do the binary search. So what will your search by? See, again, it's very logical, but you will have to decide on, like, what should be the start and end of your search. Okay, see, one thing is very clear. See the maximum in this 8. Okay, we cannot have, see, in any scenario we cannot give more than 8 candies to any child. Do you agree with me that? Because 8 is like a fixed number. Okay, let us say all the values are 8 in that case. Okay, let us say that. So 8, maybe 8 could be the answer. Okay, then one possibility is 8. Okay, that is what is the maximum in this. That could be a possibility for the answer, but we can definitely cannot go above that. Okay, for example, if I say 9, 9 cannot be a possibility itself, because okay, none of them are having 9. Okay, as such we cannot get 9 even once. Okay, as simple as that. Because remember this part, we cannot compile. Okay, we cannot merge two files. Remember that. That is the reason why, if, see, the maximum candies that you can give to a child is going to be 8. Okay, I'm just single child. I'm not saying like every child is going to get the same. I'm not saying like that. But even if you don't consider like all the child getting the same, still the maximum candy that you can give to a child is going to be 8. Okay, because only once you can allocate like a pile to a child. Okay, that's what they've given the question also, right? Yep. So you cannot assign more than two piles to a child. Okay, as simple as that. Okay, each child can be allocated candies only once. Okay, only one pile of candies. So this again is an important point. Okay, so like see what we are doing. It's going to be a very classic question of binary search. See, first of all, we're designing the search page. Okay, the left is going to start with 1 now. See, some of you will ask me why 1. See, it's going to be very simple. L cannot be 0, first of all, okay? Because, see, our answer is going to start from 0, but L we cannot start from 0. What is the reason? I will tell you that reason, because, the way that we're taking it is finally used in a division, okay? That's why this particular value cannot be 0, because if 0 comes in the division, it will create a exception, okay? Simple as that. Similarly, R we are taking as a max of candies, because at max we can give only the maximum number present in candies, okay, as simple as that. And then answer is equal to 0. This is a particular function. I will come to this later on. Just see the binary search part first, okay? So we are starting the binary search. This is very much like a typical binary search that we do, okay? So first of all, we are calculating mid. How I'm doing that, see, always I follow this approach. You have to add L plus then the difference between them, okay? R minus L divided by 2, this will give you the mid. This mid needs to be added to L, okay, to get the real mid, okay? Remember, this is just a mid, okay, but we need this mid after L, okay? So we are adding that to L, okay, as simple as that. So if you are not aware of this, please see my previous videos. I've explained in detail in that, okay? Now, once we get the mid, see, this print statement is just for your convenience. While you're submitting the code, always remove the print statements, okay, or comment the print statements. For this particular mid, I'm calling this function and passing mid as the parameter, okay? Now if if this function returns true, then this much code will execute it. If this returns false, then this much will be executed. First, let us see what is the function now. So basic idea is I'm just trying to see whether, okay, if I start distributing this much number of candies to each child, whether I will be able to distribute the same number to all childs or not. Okay, that is the basic idea I'm doing. If true, then this function will return true, otherwise false. I will again repeat. See, this much number of candies, I will try to see if I can give all the children, that is all the k children, this many number of candies. If it is possible or not. If it is possible, then the function will return true, otherwise it will return false. So see what we are doing. First one, declaring non-local key, because it's a function. It has a different scope. That's why I'm creating a non-local first. Okay, non-local means it will whenever k is used inside this function, it will refer to the value which is declared outside. Okay, this particular value, right? Yep, this particular value. I mean, okay. Now, children satisfied is equal to 0. Okay, because we'll see like how many children we can satisfy if we start giving this many candies. Okay, that is the basic idea. And then I'm going through each of the candies. Okay, I'm going through this particular array basically. Okay, the candies array, I'm going through every pile in this. Okay, every value that you're seeing is basically a pile. Okay, so I'm going through every pile. For pile in candies, what I'm doing is I am dividing. Okay, remember this is integer division. What is integer division? It means, for example, if you divide, let us say, uh, okay, let me take the case of 10 divided by 8. Okay, if you do 10 divided by 8, the answer will come as 1. Okay, it will not be like 1 point something, it will just come 1, because it is integer division. Okay, so only the integer part of the answer will be retained. Okay, it's an integer division. Where we see double divided by simple in Python, then it will be integer division. Okay, if you are following in Java, then maybe you have to convert this to integer. Okay, simple as that. So what I'm doing is, this particular division will tell me, like, for each pile, like, so for example, I equal to 5. Okay, let's say I equal to 5. That means I'm checking to see from each pile how many 5s can come. Okay, for example, in this case, if you see, what we'll do is, in this example, if you see, there is no 5 present here. Okay, 5 cannot come from this. Similarly, 5 cannot come from this, but from this there are 3 5s that are going to come. Okay, 15 divided by 5, if you do, there are 3. The answer is going to come as 3. So there are 3 5s which are inside it. Okay, so I will get 3. Similarly, I will be collecting all of them. Okay, and that will tell me how many children are being satisfied. Okay, at last, if at every instant, okay, at every iteration, I will check whether the satisfied children is greater than equal to k or not. If this is the case, that means all the children are satisfied. Then I can return true directly. I need not go for the next iterations. Okay. Otherwise, if this whole for loop completes and we have not returned true, then we have written false. Okay. That is the basic idea, and this will be printed. More than k subpiles can be created with each file is equal to I. Okay, as simple as that. So that means if we start giving I number of candies to each child, then yeah, we can satisfy them. Okay, as simple as that. But remember, the question is about maximum number of candies. The question is not about, like, any number of candies. It is about maximum. So this only helps us in deciding whether a particular number of candies can be given to every children equally or not. Okay, that is the only thing that it can do. Okay, what I'm checking is, see, if this function returns true, then that means we have got a possible answer, but it need not be the real answer. Okay, this could be a possible answer. Okay, so what we are doing is, we are just printing possible answer is equal to this. Then see what we are doing. I'm storing it to my answer first of all. Okay, remember, answer is 0. Okay, answer will be starting from 0 if this code is not executed, let us say. Okay, there will be example, I guess, in example number 2, if you see, the answer is coming 0. So what will happen is, this many candies. Okay, 2 plus 5 is equal to 7. So there are only 7 candies. Okay, even in the if you divide the to the deepest extent, still you will have only 7 heaps. Okay, I mean 7 piles. Still you cannot give equal conditions to every child. Okay, that's the basic idea. So in that case, this part of the code, okay, this part of the code will never be executed. Okay, because this function will always return false. So this part of the code will be never executed. That means answer will remain zero only. Okay, that is the basic idea, right? Now, whenever this part of the code is true, okay, whenever this function returns true, what we'll do is we'll store that as the possible answer. Okay, then what we'll do is we'll try to see if even bigger number of candies can be given to the children or not. Okay, so how to ensure that? See, what we'll do is we'll just shift our search phase to mid plus one. Okay, so the next start, okay, that is the left of the search will now be mid plus one, and we'll proceed with the same right. Okay, as simple as that. If let's say this condition is not true, okay, that means we are giving more number of candies in such a way that every children could not be given all the candies. Okay, that means let us say mid is a very big number. That means let us say we have around 10 candies. We are giving 6 candies to each. Okay, there are 10 candies, there are 5 children. So if we cannot give six number of candies to each children, right? So in that way, what we have to do is we have to now reduce the number of candies that we are giving. Okay, if this condition is running false, that means we have to reduce the number of candies that we are giving. So for that, what we are going to do, we have to shift the search phase to before the mid. Okay, that means now the right will be mid minus one and the left will remain the same. Okay, as simple as that. This will ensure that the mid that you are going to get is smaller than the current mid. Okay, because if the mid is smaller, there could be a chance that it because if you are giving less number of candies, then it could be a possibility that all the children could be given the same number of candies, right? That is the basic idea. So see, this is the code. I'm printing this thing and I'm finally printing whatever the possible answers. So let me show you some of the outputs. So as you can see, like for this example, if you see 1 1 15, so let's see what we are getting. Okay, so first of all, L equal to 1. Okay, remember as I mentioned, L will start from 1. Okay, and R will be the max of candies. Okay, in this case, R will be 15. Okay, so this is what it is, L equal to 1 and R equal to 15. So we are getting 8. We are going to see if we are we are going to get 8 candies to every children, whether it is possible or not to give all the children with the same number of candies. Okay, it's not possible. Okay, because if you get 8 to 3 children, it will be 24. Okay, but we don't have 24. As simple as that, right? Now, so we'll shift our space to, like, we will try to reduce the mid now. Okay, so what we will do, see, in this case the R will be made as a mid minus 1. Okay, if you see the next R, it is going to be mid minus 1 now. Okay, for this R, okay, L will remain the same, R will be 7. If you find the mid for this, it will be 4 now. Okay, now we will try to see if 4 number of conditions we give, whether it is going to be possible to give all the children the same condition or not. So we'll get to know that, okay, it is possible. Okay, more than k sub subpiles can be created with each file equal to 4. That means it is possible. So 4 is going to be a possible answer. Remember, we need the maximum answer. Okay, we need the maximum. This is a possible answer, but still there could be possible that we can go further. Okay, so what we'll do now, we will reduce our search phase to the previous R, but the start will be now mid plus 1. Okay, if you see, L got changed. Okay, here mid is 4, so now L will be 4 plus 1, which is 5. Okay, here L is 5, mid whatever sorry, what is the right, that will remain the same. Okay, as simple as that. R is going to remain the same. If you do with this now, okay, with this we are getting m equal to 6. Again, mid equal to 6 not possible, so we will reduce it further. Now it will be 5. Okay, we are getting now mid equal to 5. Okay, so with mid equal to 5, again we are getting a possible answer which is even greater. Okay, see, the previous possible answer is 4. Now we are getting even bigger answer, which is 5. Okay, so at last, when the whole search phase is completed, we will stick with 5 because that is the maximum possible answer that we have got among all the possibilities. Okay, so finally 5 is written as the answer. So this was the example that I have created. You can go to the other examples. Okay, you can see the outputs. See, in this case, none of them are going to be possible answers because obviously it's visible, right? There are only 7 candies. Okay, if you do it even do the deeper experiment, still you will get only 7 sub piles. Okay, still you cannot give a single pile to all the students. Okay, because there are 11 students, right? Similarly, for example number 1, you can see how it is happening. At last, we are getting 5 is the answer. Okay, prior to that, we are also getting 4 is the answer. Okay, as simple as that. So yeah, friend, that was all for this particular question. If you talk about the space and time complexity, see, this time I want you to find out how it is going to be a space complexity. Okay, so for that reason, let me call the max number of candies equal to m. Okay, let me call this particular value as m. Okay, now if I call this as m, so let us see what is happening. So this whole the binary search is going to happen from l equal to 1 till m. Okay, so binary search is going to get us log m time. Okay, so I'm writing this in front of you this time. See, so the time complexity is going to be, see, I've not calculated fully, but I'm just telling you how it works. Okay, it's going to be log m now. Okay, only the binary search part. Okay, only the binary search part is going to be log m. Okay, because we're starting from L equal to 1 till R equal to m. Okay, left and right are 1 and m. Okay, simple as that. Now for each iteration of this binary search, what we are doing is we are calling this particular function. Okay, what this function does, this function is basically going through each of the piles. Okay, that is the length of this. Okay, let us say the length of this is n. That means in each call, okay, in each call of this, basically we are going to go through all the piles in this. Okay, that is going to take O of n time. Okay, let us say the length of the condition is n, then it is going to take O of n time. So it is going to be log m into n. Okay, because for each of the log m iterations, we are going to call a function which is going to go up and down. Okay, so it is n into log m. Okay, this is the time complexity. And if you talk about the space complexity, see, I'm using some variables. Okay, that is fine. One more thing is even this part. Okay, even for finding the candies, see, I'm saying r is equal to m. Okay, let max of candies be m. Okay, don't confuse between the two. See, I'm yeah. Now, even for this, okay, even for finding the max of the candies, you have to go through all the candies once, which is again going to take off and time. Okay, so it will be something like this. Okay, n plus n log n. Okay, but since n log n is a bigger term, so you can remove the n basically. Okay, because remember, always big on notation, we are going for the max. Okay, we are always going for the worst. Okay, so you can remove the n in this case. Okay, as simple as that. Now coming to the space complexity, yeah, we are using certain variables. They are constant. We did not include them. Other than that, if you see, we are not using anything as such. Okay, we are not using any you know like array kind of structure. Okay, any other structure other than some of the simple variables. Remember, variables are going to remain constant. Okay, whatever with the number of candies here, whatever the value of k here, still this will remain constant only. So for idea here is this space use will remain constant for any value of candies or k. Okay, for that reason is going to be o of constant, which is o of 1 you can write. Okay, as simple as that. So this is going to be a time complexity n log m, and space complexity is going to o of m, where m is the max of candies. Okay, and n is the length of the candies. Okay, as simple as that. So yeah, friend, that was all for this particular video. This was the solution. I will request again, please go and see yesterday's video. That was a very nice question. That was a FANG level interview question. Please do go and try that out and see whether you are able to solve it or not. That was a really good question, by the way. Okay. By the way, there are multiple ways to do yesterday's question. And for today's question, there is not much we can do. Only with binary search we are able to solve this. There is no other, efficient, better approach or efficient approach than this. Yep, that is all I can say. So, yeah, friend, that was all for this particular video. If you talk about the, the constraints here, if you see, yeah, so K as such is not coming. If you see, no, K is not coming in the calculations. Okay, as such, K is not going to come here. Okay, but yeah, the candies value is going to be 10 power 7. Okay, each of the candy value. So yeah, the M is going to be in the range of 10 power 7. And if you talk about N, N is going to range of 10 power 5. Okay, as simple as that. So if you see one thing, the value K is not a part of either space complexity or time complexity. That is a good thing about this. Okay, so these kind of things you should be thinking first before deciding on the solution. That will help you a lot, because in this case, if you see, the smallest value is 10 power 7, sorry, 10 power 5, then 10 power 7, and then 10 power 12. Okay, so if you devise a solution which is dependent on k, then it will be worst solution because it is very high. But if you design a solution which is on this particular value, that is n, then it will be a better efficient solution. Okay, because this value is smaller, this value is even bigger. Okay, so n log n for this particular value is smaller compared to n log n for this particular value. Okay, as simple as that. So often that was all for this particular question. If you like my solution, if you like the way I'm, the quality of the content, please do subscribe to the channel. This really gives us a lot of motivation to continue further. This was my 143rd day. Okay, 143rd day. Okay, and I hope there are many more days to come. Oh, sure. Let's see tomorrow. Thank you, team.